EMI technique. So could you identify the damage location? I have not yet downloaded your reports, but I hope everyone has submitted, all groups. So what was the damage location? Which location had the damage in the experiment we had done in the lab?
For experiment number 5, sir.
Yeah.
Sir, damage location is 7.
Correct. So how did you locate that it's at 7?
Sir, we have plot the post damage post baseline signature and post damage signature. There is variation at number 7 location, and root mean square deviation is also high at that location.
Okay, correct. So the location 7 is correct. And how you have done first way is that you visually look at the two signatures. You will find some difference. And other locations you find there is negligible change. So that is visual.
Negligible.
And the other is the statistical. You find out the root mean square deviation. So that is the statistical index. But then there are issues with the statistical index. So that's why we go on impedance-based identification, because we have learned the concept of mechanical impedance. So we'll show you, if you have the equation, then you can use that equation to your advantage and go deeper. You will get deeper understanding of the structure, how the structure is undergoing change with damage. That we'll learn today. Okay, so before that, again we just see the equation, and if you see the characteristics of the two parts G and B, you'll find that the magnitude of B is very high as compared to G. It will be 1 order of magnitude higher, almost 10 times higher. But if you are seeing B, you will not see the peaks very prominently. But if you are seeing G, you will be able to see the peaks very, very prominently. So the reason is that if you go further, and if for example you make the substitutions, all you have to do is make some substitutions. I'm just using my pen, so just bear with me. So for example, here you input this as epsilon 33 1 minus delta J. Then you can also substitute this in the complex form, YE 1 plus eta J. So these two substitutions, and then you can also expand these two, Z and ZA. You can write in their respective forms X plus YJ. X is the real part, Y is the imaginary part, and here also XA plus YAJ. Then you have the term 10 KL by KL also. This you can say that this is equal to R plus TJ. So basically 10 KL by KL, this you have to find. So with these substitutions, you will be able to separate the real part and the imaginary part. And you will find, just based on the expressions, that the imaginary part is very high as compared to the real part. So in the real part, you will see a multiplying factor delta will be there in the real part. The capacity portion will be multiplied by delta. So its magnitude is reduced. So here in the case of the real part, the capacity portion is drastically reduced and the structure part is exaggerated. In the imaginary part, opposite happens. In the imaginary part, capacity portion is very high as compared to the structure portion. And what is the structure portion? The structure portion is this portion, ZA divided by Z plus ZA, D31 square YE 10 KL by KL. These are all the parameters which are related to structure. The rest of the parameters, they are electrical. So we assume that when the damage is occurring on the structure, so electrical parameters, they are not changing. Another point is that if the structure's impedance is very large as compared to the piezo, then the peaks which you are seeing here, they will be exactly the resonance peaks of the structure. All these peaks, they are the resonance peaks of the structure. Otherwise, if the magnitudes are of comparable order, then these peaks, they would also show the piezo peaks. See, there are two systems. One is the piezo sensor. Piezo sensor has its own resonance frequencies. Structure has its own resonance frequencies. So if the magnitude of the structure impedance is very large, then practically all the peaks, they will be the resonance frequencies of the structure and not the piezo patch. But otherwise, it will be a composite resonance, combined resonance, that what we are finding is that the peaks are at some frequency which might be closer to the resonance frequency of the piezo sensor rather than the structure. So this happens in some structures. Okay, so going further, now here we are showing the G and the B part on log scale. Now log scale, you can visualize better in the same graph. So main observation is that the magnitude of the imaginary part is several times that of the real part. So largely B looks like a straight line. So it looks like B is like a straight line. And both G and B, they exhibit linear variation. So if you see otherwise, they show linear variation with frequency. So don't go with this figure. This figure is on a log scale. But this figure, which is on the normal usual scale, you will see that they are linearly increasing with frequency. Why they are linearly increasing with frequency? Because there is omega. If you see the expression, omega is outside. So now we have learned 1D interaction, and we could derive the impedance model for 1D. Alright. So that I'm assuming that you are proficient in deriving for 1D. But then if you introduce more complexity, then we can have 2D interaction also. Now 2D interaction, we are not going into the derivation of the 2D interaction, though 2D interaction is also there. We can expand. Once we have learned how to model it in 1D, we can expand to 2D. And then we can also take into account the shear lag factor. The shear lag factor means the strain differential between the piezo patch and the structure because of the bond layer. So that can also be modeled. But in this course, we are not going into that much detail. But what we note in general, that most structures, they are like 2D structures. So in fact, when you say, we are saying that we are assuming that the piezo is vibrating in only one direction, that is axis 1. We are assuming that piezo is vibrating, when you are applying electric field, piezo is vibrating along axis 1. But the fact is that the piezoelectric effect is 3D in nature. So when you are applying electric field, a sinusoidally varying electric field, then the piezo will also undergo vibrations about axis 2 and axis 3 also. So all these, they are together. So especially in the 2D structures, the vibrations, the lateral vibrations of the piezo patch, they also become significant. So it's 2D interaction. So 2D vibrations, they were modeled by various researchers. So we're not going into the details. But for 2D interaction, like one of the researchers, they use the concept of cross impedances. So here, for example, because the interaction is 2D, so the force along axis 1 is related to both the velocities u1, which is along the x-axis, and u2, which is along the y-axis. Both contribute. So similarly for F2. So based on this, they derived some expression for 2D case also. We are not going into details, but they derived one complicated expression. But then if you see here this equation, if you want to find out, okay, I have derived the signatures. If you want to find out what is the mechanical impedance of the structure, you will find difficulty. See, I take you back to Liang's equation. Liang's equation is very simple. If, for example, you are experimentally measuring the admittance, so you are basically measuring two parameters G and B at a given frequency. So at a given frequency omega, you are measuring two parameters G and B. And then here, if we consider Z as the unknown, all other things, all other parameters, you can fit here the values. D31 is supplied by the manufacturer. Young's modulus is known. Then kappa can also be calculated. The mechanical impedance of the piezo patch can also be written. We have derived the expression. So except Z, Z is the mechanical impedance of the structure. Rest all are known. So we have two equations. From the measurement, we are measuring two parameters G and B, and then we have two equations, one for the real part, other for the imaginary part. So you can solve, and at the end you can find out what is the mechanical impedance of the structure, the unknown structure. This is possible in Liang's model because we have only two equations and then the unknowns are also two. But if you go to the complicated, the next higher stage where we have this kind of equation for 2D interaction, this will fail. You will not be able to derive the mechanical impedance of the structure because this system of equations is highly indeterminate. So we have a midway solution which considers both the directional interactions, and I am not going into the mathematics. Mathematics is not within our scope of the present course. I'm just giving you the expression. So here what we have done is that we have defined the impedance in such a manner that 2D interaction is automatically taken into care. So first of all, we are defining the displacement, because now what happens when the piezo patch you apply electric field, it will expand in both the directions. So what we are now seeing is that it undergoes change in cross-sectional area. So we are now defining the equivalent effective displacement in this fashion, that we are dividing the change in area by the undeformed perimeter, so that we get the dimensions of displacement. So this is called as effective displacement. But this effective displacement takes into account both the directions, because we are now changing, we are now modeling change in area with vibrations. So this helps in mathematically writing a simple equation. So this is our effective displacement. You take its derivative, we get effective velocity. So use this definition of effective velocity and you can get the effective impedance. For example, here we have the expression for effective impedance. This is the expression for effective impedance. So what we have used is, we have used the effective velocity, and then the effective force. What we are doing is, we are basically doing algebraic sum of all these forces, not directly, but in this fashion, otherwise these forces will get cancelled out. So we are doing curve integration of all these forces. So curve integration of all these forces, what will happen? They will not cancel out, they will add. So that is the effective force. So effective force by effective velocity gives us effective impedance. But this effective impedance is like 2D. It is a measure of the 2D interaction, not just 1D interaction. So finally we get an expression like this. If we are modeling the phenomena in 2D, then we have to take into account the Poisson's effect also. So Poisson's effect is now considered here. Both these stresses, they will contribute to strain in both the directions, and with this we can derive expression like this. So this is a generalized expression because it's valid for 2D case, but then here effective impedance, it has only two components, x plus y. So just these two terms rather than the previous model, 2D model which had multiple terms. So this makes this equation simple. So we can use this equation to derive the expression for x and y from the measurement. Means in the experiment we are measuring g and b. We have two parameters, we have two equations, and we have two unknowns x and y, and we can find. But this x and y will be relevant for 2D case. So this is now the comparison between the experiment and the model. So we have the theoretical values and these are the experimental values. So you will find that there is some mismatch. The slopes are not matching. So why these things are happening? Because we are basing our calculations on the parameters supplied by the manufacturer. So best is that we can find or measure our own parameters for the piezo patch. Then we can have a better comparison. So this is the previous case. For example, here these researchers, they find a lot of difference between the theory and the actual experiment. The peaks are correctly, frequencies they are matching, but the magnitudes are not matching. So what we can do is that we can get the parameters of the piezo patch little bit in some simple way. So if, for example, what we do, we derive the signature of free piezo patch. So free piezo patch means that this term is equal to 0. If you set this, then this will get cancelled out and we'll get this expression. So this is the expression for the mechanical impedance of a free piezo patch. So we use this, we can split into real and imaginary parts, and we can use this to our advantage to obtain the parameters of the piezo patch. We'll just show in the next slide. So for example, here we can take another extreme. If piezo is free, then this is 0. And then there is the other extreme, that if it's fully clamped, if the piezo is fully clamped like this, then what will be the mechanical impedance of the structure? Mechanical impedance of the structure will be like infinity. So these two extreme cases we can do, and then we can obtain the free piezo signatures as well as fully clamped piezo signatures like this. So what has happened? The free piezo signature shows these 3 peaks. So these are the 3 resonance peaks of the piezo patch, and you can also get them by the method we had described earlier, that tan KL by KL or kappa or K, whichever you can use. If you make this equal to 2n minus 1 pi by 2, sorry, KL equal to 2n minus 1 pi by 2, you will be able to get these peaks, the values of these peaks. But in the case of the fully clamped piezo, what we find, these peaks, they have totally disappeared. So actual structure is in between the two. Actual structure will be in between the two. So we'll get a peak somewhere in between. And if the mechanical impedance of the structure itself is very large, then the peaks, they will not show anything related to the piezo patch. It will be totally structure resonance. Okay, so we can do a further analysis of the free piezo signature. So we have now, these are our free piezo signatures for the real part and the imaginary part. We have just expanded these complex terms. So if you expand the complex terms, you get like this. Now we can do for very small frequencies, very small frequencies, we can do quasi-static approximation, because for very small frequencies this term will be 0. This term will be equal to, this whole term will be equal to 0. Alright, for very small frequencies. So we can make use of that to obtain some parameters. For example, what we find is that for low frequencies, these terms are 0, and we have very simplified expressions for the very low frequencies. So we have the real part and the imaginary part. So real part will be something like GF equal to 8 pi FL square by H is the thickness, and multiplied by epsilon 33 delta. and similarly will be the imaginary part. So if you are plotting these two versus frequencies, the G free and B free as function of frequency, then the slopes of these two will give you, basically slopes of these two will give you the measure of these two parameters, epsilon 33 and delta. So that will be the advantage. You can measure them. And then what we can do is that we have assumed that our piezo patch is bonded on the structure. So first we can derive its free signature. We can derive free piezo signature, and after we have done the complete updating of the model of the free piezo patch based on the parameters which we have measured, then we can bond it on the structure and then we can obtain the final signature. So this will give us a better representation of the phenomena. So what we will find is that we need some tuning, fine tuning. So we have to insert this parameter C or C1 and C2, and that helps in fine tuning, in updating the model of the piezo patch based on the free piezo signatures. So what we do matching. For example, here we have done the matching. Now the theoretical and the experimental free piezo signatures, they are matching. So this is the case where we have a single peak, and this is the case where we have twin peak. Sometimes if you see the signature of the free piezo patch, you will find twin peaks. Why twin peaks happen? Because ideally the piezo patch should be perfect square, but there may be small manufacturing defect, that one edge may be longer than the other. In that case, if the two edges they are not exactly matching, we'll have twin peaks. So to model twin peaks, we have to introduce the parameters C1 and C2 in this term. Like the term here, if you just replace this 10 KL by KL by this term involving C for single peak case and C1 and C2 for twin peak case, so we'll get the answer. So we get a better signature, and then now here is the comparison. So this is much better as compared to the previous one, because here the peaks are better matching, and here the slope is also matching. Otherwise there was a lot of difference. So now taking into account this updating of the model, finding out the measuring the parameters of the patch, we get a better representation of the structure. Okay, now these things I have covered in short. Now the main thing is, now here you can compare that earlier the signature was like this, the matching was not proper, but now the matching is much better. Now here you can see the signatures are better matching because we have accurately used the parameters of the piezo patch, and we have done updating of the free piezo patch. Now all these I am telling you just to make a background, but the main thing is very simple, and I am coming there. In fact, the derivations for 2D case we are not covering as part of the course. You take the equation as it is, and also we are not emphasizing on memorizing an equation. You don't have to memorize an equation for exam. Alright. So now the impedance-based identification, this is what is most important. Impedance-based identification means that we are not relying on anything statistical. Like you have done the identification based on the signatures. Signatures are visually changing. You say that there is a damage. The root mean square deviation is changing. You are saying that there is damage. But what is the underlying phenomena which is happening? So for that we rely on impedance-based identification. For example, here what you see, one spring and one damping element, they are in parallel. So what will be the equivalent impedance? We just use the rules of parallel impedances and we can obtain the value. So this is what will be the outcome for the expression for the mechanical impedance. So if we plot x and y with frequency, you will see the response like this. The real part is constant. So if you plot x with frequency, it will come out constant. And the imaginary part, what will be the plot of the imaginary part? Imaginary part will be like this. First of all, it's negative. and as the frequency is increasing, the negative part is coming asymptotic to 0. So this would be the variation of this system, which is a parallel combination of spring and a damper element. So in technical sense, it's called Kelvin void system. Okay. So what we have to do is we have to solve the inverse problem and try this kind of identification. So how do we do this? We have the plot of x and y. For example, in the case of our structure, let's say we have acquired the signature. Then you do inverse problem. You solve the inverse problem and try to get the value of the mechanical impedance of the structure, and then plot it, and you will be able to see that yes, it's following some pattern. So that pattern we use to identify what is the built-up of the system. So in short, what we do, we just make use of this equation. So from measurement, we are obtaining this from measurement, and then we have this equation. I'm using the 2D equation. You can use 1D equation also, that will also give something, but 2D equation takes into account the 2D interaction, so that will be much more realistic, though we are not going into the derivation. But essentially what we can get is, by solving this equation, you will be able to get what is x and what is y, and from the variation of x and y we can identify the structure. So this is called as impedance-based identification. For example, this is one block where piezo has been bonded, and this is the plot of the variation of the mechanical impedance with frequency. So if you do this analysis, you'll find that the variation of x and y will be like this. So you'll find that x is coming out to be positive, y is coming out to be negative, and the negative value is also decreasing with frequency. So that means we have identified the system like this. So this is our system. So by the values of x and y, we can even find out what is the value of k and c. So that is, we are doing an identification. We are analyzing the structure as a parallel combination of k and c, and this has been revealed by the piezo patch to us. Similarly, this is another example that in this frequency range, the signatures were like this. So this could have been possible only by this type of combination of the signatures. In fact, there is a whole set of signatures, some patterns, some standard patterns of various combinations of elements, and by that we can identify that closest which system is matching with our structure. Now, what is the advantage in damage detection? We can make use of this fact to find out how the stiffness terms, how the damping terms, they are changing with damage. For example, here for this structure, as the damage is happening, the stiffness is reducing, the damping is increasing, because that's what happens when we have damage. In general, the stiffness reduces and the damping increases. But this kind of identification gives us more parametric analysis, because earlier we are just doing visual inspection of the signatures without going into the structure part. Now here we are going deeply into the structure part. So these are some of the standard combinations. So these are expressions for some standard combinations you can derive on your own by using the rules of parallel and series combinations. So when we do the signature analysis, we find out x and y, and after this then we compare with these systems. That tells us what kind of system we are happening. Usually we get systems like this, or we get systems like this also, a series combination. So parallel and series combination, the difference is that the y you can derive yourself all these expressions, that in the case of the series combination we have the imaginary part or y going from positive to negative, and this is the point where it crosses the zero line, and this gives us the one equation, and we can find out the actual values of k C and M. So this is called as impedance-based identification. I'll give you example that this was used for fatigue life assessment of steel joints. So in fact, this is a detailed study. Earlier batches we used to do one more lecture full on fatigue, but because now in the COVID semester we have 12 weeks rather than 14 weeks, that part I'm omitting now. So here piezo patches, they were bonded, and the joints, they were subjected to fatigue type vibrations. So fatigue means that we are subjecting to them to cyclic stresses. We are taking to some tensile stress, then going to compressive stress, and so on. So even if the stress ratio is not very high, for example here we are seldom exceeding 0.6 of the yield stress, 0.6 times the yield stress. So apparently this may seem that we are on a very safe limit, but here the stresses are dynamic. So after cyclic loading, so say after several thousand cycles, the specimen ultimately breaks down. For example, this is one type of failure. So which type of failure is this? You have seen, you have learnt steel design. So what kind of failure is it? Is it tensile failure? Is it bearing failure?
Tearing failure.
Yeah, except bearing failure. The other type of failure is tensile failure. So it could be tensile failure or bearing failure.
Tensile.
This is bearing failure. This is not tensile failure. Tensile failure means that the section breaks from here. That will be the tensile failure. This is a bearing failure. So bolt has basically failed the plate in bearing. If we use the root mean square deviation, so what it gives, it only gives a statistical number, but that number does not tell us how severe is the damage. Of course, if we have lot of values, then we can say, okay, relative to the previous stage, it is having a severity level higher or lower, something like that. But then we cannot be very sure. For example, here, these are the root mean square deviation of the 3 patches. So all the 3 patches, they are located not very far from the damage. And what you see is that patch number 1 is the farthest. Patch number 1 is farthest. 2 and 3, they are located at same distance from the damage location. But you know, you see 2 and 3, the magnitude difference is very high, and their behavior is also very high, very different from each other. So root mean square deviation, we cannot say that definitely if the root mean square deviation is above certain value, then it's severe damage. We cannot classify the damage based on this. But then if you are using the impedance approach, then we have better chance, because for example here by the impedance analysis, we found that the system is identified like a Kelvin void system, a parallel combination of K and C, and this is how the imaginary part, the Y part, it varied. So imaginary part of the mechanical impedance, which we have basically acquired from the piezo signatures, so this Y part is basically a measure of the stiffness of the structure, because in this system, if we have this kind of system, then the imaginary part will be minus K by omega. And what we see here, we are seeing similar kind of behavior. What we have done is we have plotted Y as inverse of frequency, so it is more or less a straight line, and as the damage is happening, as we are increasing the number of cycles, what we are seeing, sorry, the arrow is on the other direction, as we are increasing the number of cycles, what we are seeing is that the slope is reducing. And reduction in slope is what? Reduction in slope essentially it tells us basically that your stiffness K is reducing. So we are getting a very relatable experience with this kind of identification rather than simply using root mean square deviation. Okay. And similarly for concrete damage monitoring also we have used this. For example, for concrete also the system identified is same, and we could find out the stiffness parameters. And once the concrete cube was subjected to this kind of loading, so what we find is that there is the secant modulus. What we find in concrete, we measure the stiffness as the secant modulus. For example, the secant modulus is reducing with incremental loading. So that is a measure of the stiffness. So we could very well correlate this with the equivalent stiffness. The loss of equivalent stiffness and the loss of the secant modulus, they followed more or less similar kind of pattern. Okay, so what you can do is that you can read this paper, but this is only optional. Reading is optional only. So what we have covered in short is the impedance-based approach. So essentially, to give you in nutshell, what we have done is, let me just go to the particular slide. In nutshell, you don't have to go through the derivations. So essentially what we have done is we have this equation. So what we get is that from the experiment we measure G and B from the experiment. Sorry. Sorry, it is again hanging, so give me a break. I think I need to just escape and do again. Yes, so impedance-based identification means that all we have to do is just find out from the experiment. We obtain G and B. This is from the experiment. And from the analysis you find out what are the values, the real and imaginary parts of the mechanical impedance of the structure. Then plot it. So if you are getting a certain pattern, for example, we have some standard patterns. Compare with the standard patterns. So compare with these standard patterns. For example, if you are seeing that the behavior of X and Y, which are identified from here, they are following this kind of behavior. That one part is straight. Sorry, just bear with me. That one part is straight line, no change or minimal change, and the other part is negative, and the negative value is reducing. That means your system identified is like this. Similarly, if you are getting this kind of behavior, that the real part is again constant and the imaginary part is positive and straight line, that means your system is like this. And similarly, for a parallel combination, you will get this kind of behavior. So usually these systems, they are very commonly identified, and once you identify the system, that means you have identified the structure. And this is a parametric structure identification, because you are basically measuring the stiffness, damping and mass characteristics. So this is more reliable as compared to root mean square division. So we have seen for the case of the impedance approach for these joints. For example, in the case of the joints, we could very easily identify this system, and this is confirmed if you are plotting, for example, this system. The equation is like this, that your imaginary part is minus k times omega inverse. So here, that's what we have done. We have plotted the inverse of frequency with y, and we are getting this kind of negative slope. So it's a linear relation, and as you are increasing the damage, the slope is reducing. So slope is a measure of the stiffness, so stiffness is reducing. So we could very easily correlate how much stiffness has reduced. So you have any questions on this, then please let me know. Any questions? You have any questions, then please raise your hand.
Professor, I will also add,
Yes, yes.
give me also another 3 4 minutes.
Please go ahead. You are most welcome.
See, as Professor Bala said that impedance-based approach, I would suggest in my thesis also, I have taken one chapter where I have used this technique. I have taken a beam which I had done the mixed design and cast the beam and then use that beam in the chloride saline water. And through EMI technique, through whatever Professor Bala said, the value of Z to X and Y with respect to frequency, then to see that whether these uh, parallel or in series based on what he has explained. So I have done actual experiment where I use this value, convert it to X and Y value. From X and Y value, I worked out the C, K, and M value. The entire frequency range, I mean, through FFT, I went to the time domain thing. So the time domain thing had K stiffness versus time. Due to damage, see, with respect to time damage, more and more with respect to time. Like the mass also went on, so I could get the clear picture of K, C, and M with respect to time. Where straight away you know that initially it damage less, and particularly the chloride water, which I saw that using the seawater. So as and when we use that water, the damage will go on becoming more and more. So anybody is interested, they can go through one chapter of thesis where I have highlighted everything, how to work out the damage with respect to impedance technique, where finally I said the stiffness with respect to time, what is its behavior, mass with respect to time, what is its behavior. Then of course the beam, I taken the capacity part in the lab. There are also the capacity will also get reduced. Your mass with respect to time will get reduced. Simpleness of the structure will get reduced. So by reading my full chapter on this, and whatever Professor Balla has explained, and he has already given you one article. So you go through everything, and then I think this impedance technique, you will be more clear. And so I just wanted to share my thing which I actually used, did the experiment, and got the results that with respect to time, stiffness due to more damage gets increased. With that, stiffness gets reduced. Mass also gets reduced. And the capacity of the structure also gets reduced. You are getting more and more damage. And then damage, the accelerated chloride is a function of time. So from the frequency range, I, through FFT, I converted the entire thing to the time domain and then worked out separately what is behavior with the stiffness, what is behavior with damping, what is behavior with mass, and the capacity thing actually at the lab. I went and got it that the capacity with respect to time also will get reduced. Just I wanted to share this.
Okay. Thank you very much.